In this lesson, we're going to look at how to solve inequalities. So we have an example here. The path of a toy rocket can be modeled by the equation h of t equals negative 0.09 t squared plus 0.9 t plus 2, where h is the height of the rocket in meters and t is the time elapsed after the rocket has been launched in seconds. And so the question we're going to try to answer about this toy rocket is over what time interval is the height above 3 meters. So we want to know when the rocket is at a height above 3 meters, and we want to know what time values this happens at. Okay, so here I have the graph of the toy rocket, the path of the toy rocket, so the height versus the time. And here I have the horizontal line that represents a height of 3. And so what we were trying to look for is when the height value is greater than 3. Okay, so the question is asking us when the height is above 3. So when what we're looking for is when h of t is greater than 3. Okay, so what you'll notice is that the height of the rocket, if you look at the actual graph, this part here is what we're trying to find. And so the values that you can see here is at a time of about 1.3 seconds till about a time of about 8.7 seconds, the rocket is actually above a height of 3 meters. Okay, and so in interval notation, we can write it as t is an element of 1.3 seconds to about 8.7 seconds. Okay, so we'll talk about what polynomial inequalities are before we continue to look at some more examples. So polynomial inequality, often instead of comparing two polynomial functions for equality, so in other words, looking at f of x equal to g of x, we need to compare the two polynomials in terms of magnitude. So sometimes we think, when is f of x going to be greater than g of x? Or when is f of x going to be less than g of x? So as a result, the solution to a polynomial inequality could be a value of x on a given interval that satisfies the inequality. Okay, and these intervals would be the solutions to the polynomial inequality. So for example, with the question that we looked at above, when you're looking at when the height is greater than 3 meters, it's not just one answer, it's several answers, and those answers fall over an interval, and in this case between 1.3 seconds and 8.7 seconds. Okay, so polynomial inequality results when the equal sign in a polynomial equation is replaced with an inequality symbol. So here are the inequality symbols. We have the less than symbol, greater than, less than or equal to, and then greater than or equal to. And so if you take a polynomial equation where you have one polynomial equal to another polynomial, and you replace it with one of these symbols, it becomes a polynomial inequality. Polynomial inequalities may be solved graphically in a few different ways. One way is by determining the x-intercepts of the equation, and then using the graph to determine the intervals that satisfy the inequality. And so if you have f of x, for example, if you have f of x is less than or equal to g of x, one way to solve this inequality is to make it look like an equation where everything is moved to one side. So for example, if I move g of x over to the other side, I'd have f of x minus g of x is less than or equal to 0. And so what I could do is simplify the left-hand side here, use the left-hand side to graph, and then using the graph, just figure out the intervals where the function would be less than or equal to 0. So I'd be looking at this interval and this interval here. So that's one way to solve an inequality graphically. The other way to solve an inequality graphically is to graph each of these functions separately. So I could graph f of x and I can graph g of x separately. And then I can look at when one function is lower than the other. So for example, if this parabola here is f of x and the cubic function that I have here is g of x, what I'd be looking for is when f of x actually has lower values than g of x. So when the graph of f of x is lower than g of x, and so I'd be looking at this interval right here. Okay, so those are the kinds of things that we look at when we're looking at polynomial inequalities. So here's an example. It says consider the function f of x equals x minus 3 times x plus 5 times x plus 2, and then you're asked to state the domain and range, then find the zeros of f of x, then graph the function, and then find the intervals where the function is greater than or equal to 0. So I'm going to do this on a separate sheet of paper. And so I sort of started to write out my solution. So for the example, starting with the domain and range, so I know it's a cubic function, so the domain will go infinitely to the left and to the right. and the range will also go infinitely to negative infinity to positive and positive infinity. There's no restrictions on the domain and range. So my domain is all real numbers, and my range is all real numbers as well. Okay. In terms of zeros, I'm looking for when the function would be equal to 0. So I'm going to replace f of x with 0. And so I get 0 equals x minus 3 times x plus 5 times x plus 2. And if I solve for the x-intercepts of the zeros, I get x equals 3, x equals negative 5, and x equals negative 2. And you'll notice that each of them have an exponent of 1. So these are all zeros of order 1. Okay, and then in terms of the graph, the degree of the function is 3. My leading coefficient is positive. Okay, so you can see that it's positive at the front here. The end behavior, so since it's a degree 3 polynomial with a positive leading coefficient, it's going to go from quadrant 3 over to quadrant 1. So this is going to go from quadrant 3 to quadrant 1. And then in terms of the x-intercepts, so we have 3 x-intercepts. So we have x equals 3, x equals negative 5, and x equals negative 2. And each of the x-intercepts are of order 1. And then in terms of the y-intercept, we're just going to find the value of the function when x equals 0. And if you plug it into the function, you should get negative 30. So I'm going to use all these values to actually graph my function. So I have x-intercepts at 3, and at negative 2, and at negative 5. Okay, so there's my x-intercept so far, and I have a y-intercept at negative 30. So there's my y-intercept. And because it goes from quadrant 1 to quadrant 3, I'm sort of going to sketch it. So it's going to continue in this direction, and it's going to continue in this direction. And because they're all order 1, my graph is sort of going to look like that. Okay. So there's my cubic function. I'll call this f of x. So the last question that we're going to answer, and we're going to use the graph to help us do this, is to find when the function is greater than or equal to 0. So I want to know when the graph is above the x-axis. So greater than or equal to 0 means above the x-axis or equal to 0. Okay, so if we look at the graph, there's a couple different regions where it's greater than or equal to 0. So the function is above the x-axis and equal to 0 in this interval here. So this goes from negative 5 to negative 2. And then it's also greater than or equal to 0 in this last interval here, which is from 3 onwards. So we have two intervals where the function is going to be greater than or equal to 0. So in interval notation, I would write x is an element of, and now because it says greater than and equal to 0, I'm going to use square brackets to indicate that my endpoints of my intervals are actually included. So my first interval goes from negative 5 to negative 2. But because it says from the function has to be greater than or equal to 0, negative 5 is when the function is equal to 0, so it's actually included in the interval. Same with negative 2. Negative 2 is when the function is equal to 0, so this is also included in the interval. But we have a second interval where the function is greater than or equal to 0, so I'm going to add u for union. So this means in addition to. And the second interval goes from 3 to positive infinity. So I'll start by writing 3 to positive infinity. And again, because 3 is when the function is equal to 0, it's included in the interval, so I use the square bracket. And then infinity doesn't have a limit, so I use round brackets. Okay, so there's an example of solving a polynomial inequality. So looking at when the function is greater than or equal to 0 using a graph. So essentially the polynomial inequality that we just solved is actually x minus 3, x plus 5 times x plus 2 greater than or equal to 0. That's the inequality we just solved. Okay, for the second example, we're going to use the graph below to write the x-intercepts, the intervals of x for which the graph is positive, and then the intervals of x for which the graph is negative. So let's start by looking at the x-intercepts. So all we're looking for are the points where the graph crosses the x-axis. So starting with our first x-intercept, we have an x-intercept at negative 2, at positive 1, and at positive 3. So we have x equal to negative 2, x equal to 1, and we have x equal to positive 3. So there's our 3 x-intercepts. Part B says the intervals of x for which the graph is positive. So we're looking for the parts of the graph where the function is just positive. Okay? So, or in other words, we're looking at f of x is greater than 0. Now, because we're only looking at parts of the function where it's positive, I'm going to look at where the graph is above the x-axis. So for part B, we can see that our first interval is this one here. So that's from negative infinity up until negative 2. And so I'll use round brackets for the negative infinity. And then I have negative 2. Now, to figure out what kind of brackets you need here, you have to think about whether or not this value is included in the interval. And since the question asks us only where it's positive, so only where it's greater than 0, negative 2 is actually where the function is equal to 0. So it's not included in the interval. So I'm going to use round brackets. And then you can see that there's a little bit more space here where the function is greater than 0 as well. So there's definitely more than one interval. And now you might be tempted to just write from 1 till positive infinity as your second interval. Now the problem with that is that 1 to infinity includes the number 3. And at 3 here, the function is not actually greater than 0. It's not actually positive. It's actually equal to 0. So what you would have to do for a question like this is actually break this up into two intervals and look at 1 to 3 separately from 3 to infinity. Okay? It would have been different if the question said greater than or equal to 0, because then, yes, you could have said from 1 to infinity. But in this case, because you're only looking at where it's positive, you can only go from 1 to 3 and then separately from 3 to infinity. So it's actually 3 separate intervals that we're looking at. So the second interval goes from positive 1 till positive 3. So that's where the function is only positive. And then the last interval is from 3 till infinity. So it goes on forever. Okay? So that's where the function is positive. Okay? So 3 separate intervals where it's positive. In terms of where the function is negative, so for part C, you're looking at when f of x is less than 0. So you want to know only where the graph is less than 0. And you'll see here that there's only one interval where the function is below the x-axis or where it's negative. So in this case, we only have one interval, and that interval extends from negative 2 all the way till 1. And because, again, we're looking at where it's negative only, you'd use round brackets because at x equal to negative 2 and at x equal to 1, the function is actually equal to 0 and is not less than 0. Okay? And that's pretty much it.